So today I gonna ended the papers, which is about the resolving thermoelectric paradox in superconductors. And we have introduced the introductions and the result in the present videos. And now I'm going to share with you the discussion part. So to compare the major values of the thermal flux with theory, we take into account the following aspects of our experiments: the thermal resistance of the wire of substrate interface. For our aluminum flames was negligible because the thickness H equal to 18 nanometers, which was much less than the phonon wavelength. Lambda p equals is bigger than 200 nanometers at T is smaller than 1.2 Kelvin, where the speed of sound is around 5 times thousandths. The phonon temperature in such films is close to the substrate temperature, and the temperature is equals to the substrate. And the phonon terms in the differences as seen in equation 2 can be neglected because the substrate temperature is estimated to be lower than the quasi-particle temperature. Therefore, the difference in temperature could be seen as the quantum, the phonon term. Second, to calculate the effective inductance, we consider the aluminum the hot contact as essentially a weak link within a biomedical loop. This is justified because the gap in aluminum is much smaller than in the lead. The kinetic inductance of such a link is given by these following equations, where IC is the critical current. The absolute value of thermoelectric flux at temperature close to critical is equal to the very complicated formula because the kinetic inductance at the hot end acquires large values, which is not bigger than L2, when the critical current approached zero at temperature equals to critical temperature. At temperature below critical, the value of the thermal flux can be written as the very complicated formula, with scaling factors describing the decrease in quasi-particle concentrations, the electron-phonon interactions, and the decrease in the kinetic inductance. The experimentally measured value fitted with the theoretical curves are shown in figure 3b. We use the calculated value L2 equals to 10 minus 10 H for the geometrical inductance of our biomedical loops. The cross-section S equal to 6 times 10 minus 14 millimeter squares, and the length L is equal to 5 times 10 minus 5 meters, and critical temperature is about 1.2 Kelvin. Using a typical value of the electron mean free place, L, which is about 50 nanometers, and the wavelength of phonons in our aluminum films calculated above. One would expected the films to belong to the strong disorder limit, with the electron-phonon interaction described by n equals to 6 However, as known in the supplementary materials, the result of feed with n equals to 5 do not differ much from that with n equals to 6 in the investigated temperature range. Both of the feeds give the value of the products of the thermal power alpha n and the electron-phonon interaction parameters in the normal states. Using the sample-dependent values of alpha n is a realistic range, which is from 2 to 6. We obtain the sample-dependent values of sigma n in the range of 20 to 2 to 50, which is an agreement with previous measurements. To fit the dependencies of the thermal flux on temperature, we have taken the dependencies of critical current at the hot contact in the form, with the fitting parameters values of I0 equal to 30 microampere, which is realistic for our wires. In conclusion, we developed a methodology allowing the separations of the genuine thermoelectric flux from spurious sigma effect. Theoretically, we deduce the formula for the circulating currents by minimizing the total energy of the system. We solve the heat equations for the loop and calculate the thermoelectric flux using the relationship of the circulating currents to the heat flow and the energy transfer rate from quasi-particles to phonons. The major values of the thermoelectric flux agree well with the theory. The technological and theoretical advance reported here opens a new avenue for explorations of thermal phenomena in superconducting device, which is critical for energy management in nanoscale structures. Okay, and now I'm going to share the materials and method. And the first part is the metric with hydride. The hydride is especially suitable for this experiment. Its fabrication technology and compositions are compatible with the other elements, which allows the whole structure to be placed on the same chip. This avoids the use of microscopic leads to connecting the bimetallic loop and the magnetometers, thus preventing straight signal pickup and the introductions of parasitic inductance. The device is designed to reduce coupling of the flux-sensitive loop with the measuring electronics. The normal segment of the flux-sensitive loop makes contact with the measuring wire AB at a single point. As a result, the current noise is not transferred to the interferometer loop from the measuring circuit. To reduce inductive coupling of the flux-sensitive loop with the measuring circuit, the AB wire was folded. Furthermore, the device was designed to make the voltage between the N and S interface negligible, thus reduce the Jessup radiations and extra noise that are typical in standard squid-based magnetometers. The interferometer proved to be a sensitive probe for magnetic supercurrents. The total magnetic flux in equation 3 threading the interferometer loop was equal to the following equations, where B is the applied magnetic field. A1 and L1 are the area and inductance of the interferometer loop, respectively. I is the Joseph screening current in the interferometer loop. To avoid hysteresis, the hybrid was designed so that the screening factor was less than unity. The measured values is this region was independent of the screening current because it completely vanished at the extrema. Calculating the currents using quantizations of flux through the biometric loop, we arrive at equation 5 for the measured values B. The biometallic loop was made of lead and aluminum with critical temperature 77.2 and 1.2 Kelvin respectively. Thus, the concentrations of quartz particles in lead was negligible in the investigated temperature range from 0.25 to 1.1 Kelvin. The structure consists of 5 layers. The first layer was silver. The second, spacers made of silicon monazite. The third, upper silver layer. The fourth, the aluminum, and the 5 leads. The deposition was performed in medium vacuum of 10⁻⁻⁶ torr. To avoid a clean interface for good electrical contact between the layers and good thermal contact with the substrate, we use in situ argon plasma H, the thickness of silver, aluminum, silicon monoxide, and the layers was 50, 80, 30, and 150 nanometers. The areas of measurements and biometrically loop were A1 equals to 380 and A2 equals to 170. To apply magnetic field in a wide range, we use a superconducting solenoid. For fine field tuning, a wire made of lead was fabricated on the same chip. The measurements of the resistant arc were made using standard low-frequency logging technique. To provide optional operation of the magnetic matter, the length of the CD wire was made smaller than the electron phase breaking length, where D is the diffusion coefficient and tau is the electron phase breaking time. However, LCD was large enough to suppress the Joseph current, so that to avoid hysteresis. This requirement defined the values of the resistance of the LCD wire and RCD. The resistance of silver was which gave typical values of the resistance around 10 omega for a given material and wire dimensions. The resistance of LAB wire R0 is our interferometers was close to RCD. The value of R over R0 was in the range 2 to 50%, depending on the dimension of the wires, and according with theory and previous experiments. Okay, so I have to stop all this article by here because it's too difficult for me to understand all of them. Hope you would like it. Thank you and bye.